Calculation of limits. Several basic general facts about limits are helpful in the calculation of specific limits. Let's assume that the limit as x approaches a of f of x and the limit as x approaches a of g of x each exists. Then the following things are true. 1. The limit as x approaches a of f of x plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. That is, the limit of the sum is equal to the sum of the limits. 2. The limit as x approaches a of a constant c times f of x is equal to the constant c times the limit as x approaches a of f of x. 3. The limit as x approaches a of a product f of x times g of x is equal to the product of the limits, the limit as x approaches a of f of x times the limit as x approaches a of g of x. 4. If the limit as x approaches a of g of x is not equal to 0, then the limit as x approaches a of the quotient f of x divided by g of x is equal to the quotient of the limits, the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. 5. If the limit as x approaches a of f of x is not 0, while the limit as x approaches a of g of x is equal to 0, then the limit as x approaches a of f of x divided by g of x does not exist. This is because, while the numerator is approaching some number other than 0, the denominator is getting smaller and smaller, and so the quotient is simply getting larger and larger. 6. If the limit as x approaches a of f of x and the limit as x approaches a of g of x are both 0, then the limit as x approaches a of f of x divided by g of x may or may not exist. We'll soon see that this situation is where most of the interesting limit problems are. While these are stated in terms of the limit as x approaches a, they are also true for one-sided limits as x approaches a. That is, the limit as x approaches a from the left and the limit as x approaches a from the right. We have the following limits regarding two specific very simple functions. The limit as x approaches a of a constant function c is equal to c, and the limit as x approaches a of x is equal to a. Now let's look at an example involving a typical polynomial. The limit as x approaches 2 of 2x cubed plus 3x plus 5. We begin by using the fact that the limit of the sum is equal to the sum of the limits in order to calculate this limit term by term. Next, we use the second property on the previous page, which said that the limit of a constant times a function is equal to the constant times the limit of the function. This allows us to bring the coefficients of the polynomial outside the limit in the first two terms. Next, we use the fact that the limit of a product is equal to the product of the limits to write the limit as x approaches 2 of x cubed as the cube of the limit as x approaches 2 of x. So now we have our limit expressed in terms of limits of very simple functions, which we evaluate as follows. And after a bit of arithmetic, we arrive at 27. Now notice that the result is simply the value of the polynomial at x equals 2. In fact, this always happens with polynomials. That is, if p of x is a polynomial and a is any real number, then the limit as x approaches a of p of x is equal to p of a. That is, the limit as x approaches a is equal to the value at a. We refer to this as the continuity property of polynomials. We call this the continuity property because it actually does imply that the point a comma p of a, as well as the behavior of the graph near that point, are just as they should be in order for the graph to be continuous there. We'll have a lot more to say about continuity in general in a later lecture. Here's an example involving a rational function whose denominator does not approach 0. Let's look at the limit as x approaches 3 of 2x squared minus x plus 2 divided by x squared plus 1. Notice first that, as x approaches 3, the denominator will approach 9 plus 1, or 10, which is not 0. Therefore, we can attack this problem by taking the limit of the numerator and dividing by the limit of the denominator. Since those are polynomials, that's an easy thing to do. We simply have the value of the numerator at 3 divided by the value of the denominator at 3, and so the limit here ends up being 17 divided by 10. Again, notice the result is simply the value of the function at x equals 3. In fact, this always happens with rational functions provided that the denominator isn't 0. If p of x and q of x are polynomials, and q of a is not equal to 0, then the limit as x approaches a of p of x divided by q of x is equal to p of a divided by q of a, which is simply the value of the rational function at x equals a. This is similar to the continuity property that we just saw for polynomials. In fact, it's the same thing, so we have here the continuity property for rational functions as well. Limit equals value wherever the function is defined. Here's an example involving a rational function whose denominator approaches 0 while its numerator does not. Let's look at the limit as x approaches 1 of 2x squared minus x plus 2 divided by x cubed minus 1. Let's think about what's happening when x is close to 1. When x is close to 1, the numerator is approximately 2 times 1 minus 1 plus 2, or 3. And when x is close to 1, the denominator is close to 0. So when x is close to 1, we're dividing something close to 3 by a very small number, which will produce a very large value. And the closer x is to 1, the larger those values will be. Therefore, the limit as x approaches 1 of this rational function does not exist. And this is all because the limit of the denominator is 0, while the limit of the numerator is not 0. Can we say something about one-sided limits here? Let's look at the limit as x approaches 1 from the left. If x is close to 1 and less than 1, then the numerator will be approximately equal to 3, and the denominator will be approximately equal to 0 and negative, because x cubed will be less than 1. Therefore, the function has negative values just to the left of 1. So we can conclude that the limit as x approaches 1 from the left is equal to minus infinity. Now let's think about the limit as x approaches 1 from the right. If x is close to 1 and greater than 1, then again the numerator is approximately equal to 3, and the denominator is approximately equal to 0, but now the denominator is positive. So the value of the quotient will be large and positive when x is just to the right of 1. And so we conclude that this right-sided limit is equal to plus infinity. In fact, the graph of the function looks like this. Notice that there's a vertical asymptote at x equals 1, and as x approaches 1 from the left, the values of the function are negative and getting larger and larger, and as x approaches 1 from the right, the values are positive and getting larger and larger. Let's recall the last of the 6 facts with which we began. If the limit as x approaches a of f of x and the limit as x approaches a of g of x are both 0, then the limit as x approaches a of f of x divided by g of x may or may not exist. It is this situation that is the most interesting and, in fact, is the main reason why we're discussing limits at all. Computation of limits in this 0 divided by 0 case often involves use of the following additional fact about limits. Let's call it property 7. If f of x is equal to phi of x for all x near but not equal to a, then f of x and phi of x have the same limit as x approaches a. Here, think of phi of x as a simplified version of f of x whose limit as x approaches a is easy to determine, such as a polynomial or a rational function whose numerator and denominator do not both approach 0. Example. Let's find the limit as x approaches 1 of x cubed minus 1 divided by x squared minus 1. The first thing we'll do is try to simplify the function. To do that, we'll first factor the numerator and denominator. Using a formula for factoring the difference of cubes, the numerator becomes x minus 1 times x squared plus x plus 1, and factoring the denominator gives us x minus 1 times x plus 1. We can now cancel the x minus 1 factor from the numerator and denominator. This tells us that the original function is the same as x squared plus x plus 1 divided by x plus 1 for all x other than 1, where our original function was undefined. Therefore, since these functions agree for all x near 1, they will have the same limit as x approaches 1. And the limit of our new function is very easy to find since the denominator of that expression does not approach 0. So the limit is equal to the value of the numerator at 1 divided by the value of the denominator at 1, and we find that the limit is 3/2. This is the graph of the function. Notice that there's a hole in the graph at the point 1, 3/2. This is because the function is undefined at 1, and its limit as x approaches 1 is 3/2. Another example. Let's find the limit as x approaches 0 of x plus 3 squared minus 9 divided by x. Again, we begin by simplifying. We expand the product in the numerator to obtain x squared plus 6x plus 9 minus 9 divided by x. Notice now that x is a factor of the numerator, so we can cancel the x and conclude that the original function agrees with x plus 6 for all x other than 0. Therefore, these functions have the same limit as x approaches 0. So now we can easily see that this limit is equal to 0 plus 6 equals 6. Here's the graph of the original function. Notice that it's just the line y equals x plus 6, but with a hole at the point 0, 6. Another example. Let's find the limit as x approaches 2 of 1/2 minus 1 over x divided by x minus 2. Again, we begin by simplifying. Let's first multiply the numerator and denominator by 2x, which gives us x minus 2 in the numerator divided by 2x times x minus 2. So we can now cancel the x minus 2 factor, and we're left with 1 divided by 2x. So our original function agrees with 1 over 2x for all x other than 2. Therefore, these functions have the same limit as x approaches 2, and it's easy to see that the limit as x approaches 2 of 1 over 2x is 1/4. Now here's the graph of the original function. It's the same as the graph of y equals 1 over 2x, except with a hole at the point 2, 1/4. Another example. Let's find the limit as x approaches 2 of x squared minus x minus 2 divided by x squared minus 4x plus 4. Now before we begin, let's look at the numerator and denominator separately. Note that the value of the numerator at x equals 2 is 4 minus 2 minus 2, or 0, and the value of the denominator at 2 is 4 minus 8 plus 4, which is also 0. So this is yet another example where the numerator and denominator both approach 0. So let's simplify this function by factoring the numerator and denominator. We obtain x minus 2 times x plus 1 divided by x minus 2 squared. So now we can cancel an x minus 2 factor, which leaves us with x plus 1 over x minus 2 for all x other than 2. So notice now that the denominator still contains an x minus 2 factor, and therefore the denominator still approaches 0 as x approaches 2. But the numerator no longer approaches 0, it approaches 3. Therefore, this limit does not exist. So let's have a look at the one-sided limits. Let's look first at the limit as x approaches 2 from the left. When x is close to 2 and less than 2, the numerator will be close to 3, and the denominator will be close to 0 and negative. Therefore, the quotient is very large and negative, and so we see that the limit as x approaches 2 from the left is minus infinity. Now let's look at the right-sided limit as x approaches 2. When x is close to 2 and greater than 2, the numerator is again close to 3, and the denominator is close to 0, but now it's positive. And so the quotient is going to be large and positive, which tells us that this limit is plus infinity. Here's the graph of the function. Notice there's a vertical asymptote at x equals 2. As x approaches 2 from the left, values of the function are negative and getting larger and larger. As x approaches 2 from the right, values of the function are positive and getting larger and larger. For the next example, we will need an additional fundamental limit. If a is positive, then the limit as x approaches a of the square root of x is equal to the square root of a. In other words, the limit is equal to the value of the function at a. Also, the right-sided limit as x approaches 0 of the square root of x is equal to 0. So again, the limit is equal to the value. Note that we can only talk about the right-sided limit at 0 because the function is undefined for x less than 0. This is another continuity property, this time for the square root function. It says that limit equals value everywhere in the domain of the function. Example. Let's find the limit as x approaches 1 of the square root of x minus 1 divided by x minus 1. Observing first that as x approaches 1, the numerator and denominator both approach 0. The algebra that we need to do here involves rationalizing the numerator. We'll multiply the numerator and denominator by the square root of x plus 1. That gives us x minus 1 in the numerator, and the denominator is x minus 1 times the square root of x plus 1. We can now cancel the x minus 1's, and we're left with 1 over the square root of x plus 1 for all x not equal to 1. Therefore, these functions have the same limit as x approaches 1, and it's easy to see that this limit is 1 over the square root of 1 plus 1, or 1/2. Non-existent one-sided limits. We have seen that limits fail to exist when the corresponding one-sided limits don't coincide, but in all the examples we've seen so far, non-existent one-sided limits have been assigned one of the symbols plus or minus infinity, which coincides with the graph of the function having a vertical asymptote. So is there ever a situation when that is not possible? The answer is yes, but it can happen with a rational function. A simple example is provided by the function f of x equals sine of 1 over x. Here's what the graph of f looks like. Notice the strange behavior near x equals 0. If we zoom in and look at the graph on a smaller interval, we see something similar. In fact, no matter how small the interval is on which we look at the graph is going to look essentially like this. As x approaches 0 from either the left or the right, f of x oscillates between minus 1 and 1 infinitely often, thus neither one-sided limit at 0 can exist. Moreover, since the function values are bounded between minus 1 and 1, it makes no sense to say that either of the one-sided limits is plus or minus infinity.